So, I'm Maggie. Welcome to Physics University. Today, I'm going to be reading a paper and a pop science article. So, a little context. My granddad loves that I'm a physicist, and he sent me this article about some new physics thing that had been discovered and published that he was interested in my opinion on. And I wanted to use stream time to actually look at the piece and talk about it. Because I'm a little, let's just say, pop science articles are good and like they are a very important part of science communication. But they also tend to be a little sensationalizing. And I mean, this is because one, authors are trying to get people to read their content, and so they're going to, oh my god, my glasses are so crooked. I can't even. Okay. Authors are trying to get people to read their content, but it's also really hard to communicate a scientific discovery or the context of new science to the general public. And a lot of times I will be like browsing Reddit and I'll be on like Our Futurology or something. And there are these articles that are just super sensationalist. And they make it sound like the world is just going to be totally different and awesome. And like that's cool, but I always go in a little bit skeptical because I feel like as the public we need to like temper our expectations because science takes a while. And so what I was going to do is read the pop science article, see how I feel about it. And then I also have the actual paper pulled up written by the physicist that was interviewed for this pop science article. And so I want to go through the actual paper after we read the first piece. Anyway, so we'll see how this goes. I glanced through the piece before, but this is kind of a cold read for me. I haven't really looked in depth at this, so without further ado, let's get going. Pull this up. Okay. Already from the title, I'm like, A rebel physicist has an elegant solution to a quantum mystery. Anytime, like, rebel is such a sensationalist. I don't know. Maybe this person is a rebel. Let's see. The theories we have to describe the nature of the universe are completely incompatible. Enter an eccentric Polish physicist with a possible solution to the biggest of conundrums. Okay. I don't know very many Polish people, but the ones I do know are pretty eccentric. And they're also pretty good scientists, so see how this goes. Andre Dragan is not one for following rules. As a photographer, he uses extensive post-production. Okay, so this person is an artist too, which is super cool. Andre Dragan is a photographer. His main job as a physicist at the University of Warsaw in Poland, railing against conformity is not always appreciated. I mean, yeah, that's how the science community goes. Particularly when those ideas might rock the two pillars that form our fundamental understanding of the world: general relativity and quantum physics. Okay, so two pillars. Yeah, I mean, one of the issues with physics is this incompatibility, or I don't even want to say incompatibility, but yeah, I don't, they just don't touch. this idea of relativity and quantum mechanics, because like relativity happens on such a grand scale, quantum mechanics happens on a tiny scale, and so like they're not they're not in the same regime. These theories are the crowning achievements of modern physics. They describe nature exquisitely but separately. Again, because they deal with different grain size. General relativity handles big familiar objects, events in the universe. Quantum mechanics covers invisible, strange microworld. Subatomic particles can tunnel through barriers they have no business getting past. Where two particles thousands of light years apart can instantaneously respond to each other's motions. Okay, so this I understand that the author is trying to be descriptive and fun, because like that's what you have to do when you write. This is just a personal qualm, but I get a little miffed when I see people talking about quantum physics like it's absolutely just like mind-blowingly inaccessible. Like no one can understand this. It's it they have no business doing these things. And yes, from a macro scale, absolutely. The idea of an electron tunneling is really upsetting, but that's why quantum mechanics exists. Like that's why we have developed a model that describes these sorts of phenomena and is consistent within the model. And so it's not to say that it isn't surprising, but I feel like I might get lambasted for saying this. Quantum mechanics isn't hard. Quantum mechanics, like if you can do linear algebra and you can do matrices, quantum mechanics might be one of the easiest physics subdisciplines that there is. Of course, I'm biased because I like it and I feel like I'm good at it. But I'm only good at it in comparison to like electromagnetism. I hate ENS. Don't like vector calc. Anyway, but like it's cool, but it's not impossible to understand. And so I always get a little like grumpy when people talk about quantum as like this untouchable, unknowable, eldritch thing. Okay. Most of the time, the setup works well. If you're looking at how a massive star's gravity bends light, you'll whip out your general relativity textbook. Yep. If you want to understand how electrons move through a computer chip, you'll need your quantum book. Yep. There are times when a bit of both is called for. Trying to understand what happens in the very first moments of the Big Bang or what goes on in black holes. This is true. This is how, I mean, this is what a lot of particle physics is using relativistic things with quantum-sized particles. Because they're moving really, really fast, and you have, like, different reference frames, which is relativity stuff. But then you also have, like, little guys, little leptons. Hello. Hi, Brandon. Good. Talking to myself about pop science. Um, so, in these situations, a glaring problem comes into focus. General relativity and quantum mechanics appear completely incompatible. The smooth, continuous universe, general relativity describes, conflicts with the discrete, chunky one of. Okay, I like this. I like this line. Because yeah, general relativity is all about like space-time being a manifold. It is this. I mean, we use the word fabric of space-time. It is continuous, differentiable, everywhere thing. And quantum mechanics is, I like that word, chunky. It's chunky. It's discrete. It has these spikes. That didn't make sense. It's, I mean, that is one of the hardest things about quantum mechanics, if you're taking a quantum course, is the transition between talking about discrete quantities in quantum mechanics. So talking about things like spin or things like angular momentum, and then moving into the continuous regime. Like, how do you talk about the quantum position of a particle? Because position's a continuous quantity. So like, it gets tricky. Yes, please. Food in the fridge. Someone got me food. To try and reconcile them, physicists generally assume that quantum mechanics is more or less a true description of nature and then tinker with relativity to get it to match up. I disagree with this a little bit. I think maybe they're getting at the idea that gravity as a force is not as well understood on a quantum level. This is where like quantum gravity theorists are, which this approach has given the world rich, complex ideas like string theory. Okay. But has also left physicists frustrated and unable to match juggernaut equations of reality. So that, I think, is talking about that there's not like a unified field theory yet. Like, there's not a way to, we haven't found a way to mesh gravity as a force, even though we found a way to mesh electromagnetism and the weak force and the strong force together. It's a length scale thing. Like, you have to get tiny to see where these forces are indistinguishable. Draken comes at this problem from a different angle, attempting to describe nature through the lens of relativity. Okay, so I like this. This is a relativity first approach rather than a quantum first approach, which is pretty cool. Decades before he started pondering Einstein's first theory describing space-time, quantum mechanics was already well established. Quantum field theory, which forms the basis of our modern understanding, unites quantum mechanics and special relativity, but it does so in a way that regards them as two independent, distinct pieces of a wider. Reagan felt that this connection runs deeper. It's more than just being a part of quantum field theory. It's more profound. It's almost as if quantum theory does exactly what relativity allows and not a bit more. He began to dig into the maths. Oh, you know this was written by someone from like Great Britain. Okay, special relativity's equation allows for two branches of solutions. One that leads to the familiar world where matter travels below the speed of light, and another where it always travels faster than the speed of light. So, yes, the equations for special relativity, give you a, I could draw it of, so no, you're fine. So space, so space-time diagrams, which we draw in special relativity. Sorry, this is a very ugly axis. So we put space and time. They're weird because we put time on this axis and space on this axis. No, we don't. So everything is always moving forward in time. Move forward in time. I'm actually going to call this CT because we're using units of the speed of light. And then the thing with the slope of 1, which means something that moves 1 unit in space per 1 unit of time, that's light. So this is what we would call the world line of the photon. And so anything in this regime here is something that is going farther in time than it does in space, meaning it's slow. It doesn't travel, for example, a line like that. If that's me, I travel a little bit in space, and it takes me a long time to do it. So this is where like all physical objects, all massive objects exist. If you hold still, then your world line just goes straight up because you're moving in time. Time is passing, but you physically are in the same spot. And so all of special relativity is basically comparing different space-time diagrams like this for different reference frames. And so what this pop science article is implying is that this regime here is what the physicist in question is going to be exploring, where this is saying I go farther in space. Instead of going 1 unit in space for 1 unit of time like light, I go more than 1 unit of space per unit of time. So this would be like faster than light. This is the faster than light zone. And nothing physical we know of exists here. Some people will, like, there are theoretical faster than light particles, like tachyons and stuff. Yeah. Star Trek didn't. Actually, I don't know if, like, Star Trek called it a tachyon first, and then physicists adopted it. That would be an interesting piece of history. So it looks like this is the area that we're going to be talking about with this paper. Another where, okay, 2 branches of solutions. One that leads to familiar world, nothing travels above the speed of light. The other where, always faster than the speed. There's no physical evidence that anything can travel faster than the speed of light. Yep. Because the only thing without mass is light, and it goes the speed of light. But mathematically, these solutions are still valid. Sure, they're still valid. Like, Reagan thought, why not keep faster than light solutions and see what happens? When he did, he uncovered a world that looks more familiar to quantum theorists. Okay, this is interesting. So it is not uncommon when doing a physics solution to throw out an entire class of solutions because they're not useful, because they're not descriptive of reality. And like in intro physics, if you do a kinematics problem, like you're trying to figure out what time, if you throw a ball, what time is it going to hit the ground? You will get 2 solutions to that. You'll get one where it hits the ground, and you'll get another one that is like a negative time. A negative time because you have to take a square root in that solution. So you'll get a positive time, you'll get a minus time. And both of those solutions are describing things. Like, if I throw my ball in time, it will hit the ground eventually. But if I take that trajectory and track it backward, it would have been on the ground in the past if I, like, project back in time. And so negative times are kind of nonsensical My ball didn't exist there in the past. It's starting in my hand and I'm throwing it. But so we just like throw out that whole solution. So like you can explore them. You can explore the solution space. It could be really interesting, but it might not be relevant in all physics, not just these two relativity regimes. In this world, instead of a particle following a well-defined path, its motion is hard to pin down, described by complex layers of probabilities that correspond to different possible outcomes, which is known as superposition in quantum physics. Okay, so this was a jump. Like, I'm a little bit, like, jarred from how, like, abrupt that language changed. And so I don't know, like, this paragraph, moreover, if a physicist in this world tried to measure certain properties of this particle multiple times, they would not get the same result every time. Outcomes can be random, just as they are in quantum mechanics. I wouldn't say that quantum outcomes are random. I would say they're probabilistic. But the jump between these paragraphs was really jarring for me. And I want to think about why. Different possible outcomes. Okay, so like the idea of different outcomes or having multiple paths, things. Yeah, that's quantum. But I'm not getting the connection. How this relates to the faster than light solutions of special relativity. Described by layers of complex probabilities that correspond to different possible. Much like what is known as superposition. I guess I just don't like that sentence. Like, yeah, that's kind of what superposition is. But also the author didn't define what superposition is for the reader, so it kind of just feels like they're throwing around jargon. Which again, I mentioned, this is like, it's hard to write a pop science article. Who is your audience? How much education in this field do you anticipate them having? For me, I don't know. I don't feel too great about it. And I imagine that someone who has never taken a quantum class in their life would either be really overwhelmed or like mildly like confused or almost like affronted that the author is being, I don't know. I just don't like this. We can keep moving. In essence, Dragon had shown that in a world ruled by special relativity, counterintuitive quantum effects don't have to be accepted as fundamental. In other words, okay, this is also weird. In essence, so like, I tried to tell you, in essence, this is what I tried to tell you, but also, in other words, this is what I tried to tell you. This author is trying really hard to say something. I get the feeling that they just don't know how to say it. I'm trying to say it like 5 different ways. By including the wacky, unphysical parts of special relativity's equations. Okay, what the sentence? Patently random and distinctly quantum-like phenomena emerge naturally. Okay, like this, that's all that they needed. Like this entire thing could have been gone. Like this is unnecessary. Just tell me this. This line is good. A few months later, realizing the enormity of what he discovered. Every physicist thinks they've discovered. mean that kind of as a joke. I mean, I don't know this scientist, so like I don't know who they are. Okay. Reagan got these thoughts and calculations down on paper and submitted work to a scientific journal, but the manuscript got rejected twice. I got completely disappointed by this. Just thought, I'm not going to bother anymore. I'm going to leave it behind. Okay, so this actually is like, this is not an uncommon thing. Like, getting your papers rejected as a scientist is a thing that happens, and it's shitty. It sucks. But it's not an uncommon thing. Getting rejected twice, I don't know. I don't know what kind of comments that the peer reviewers gave, or what it was about the initial manuscripts that they didn't think was robust enough. But like getting rejected, it's gonna happen because academia is kind of awful and cutthroat. Got disappointed. Dragon moved from the disappointment, working on computing. Okay. Then he met Archer Eckert, and Eckert is figure in quantum information and pioneer quantum cryptography, who holds dual professorship at Oxford and. Okay, so they started a collab. Became friends. Dragon shared his ideas. Eckert liked it. Eckert encouraged and assisted Dragon to go further and see if it still worked in real world four-dimensional space. Okay, so that description is making me think that the initial stuff or the initial paper was only in that like 2D space, only in a like space and a single time. Sorry, a single space dimension and one time dimension, which you send to 4D space time. Like two jazz players. Um, so then they wrote a paper summarizing their new. I have that pulled up as well. With memories of rejection swirling in his mind. This is so dramatic. Dragon gave Eckert one final opportunity to back out. Are you afraid? You're not afraid to endanger your reputation. Eckert was blunt in his response. Screw reputation. This is so drama. And again, like I understand that as an author for Wired, you have to. Condé Nast expects to be a little like dramatic and have flair, but I don't know. I don't know. Maybe the paper's super mind blowing. I haven't read it yet. We'll see. Unlike Dragon's previous solo attempt, the paper passed through the first test. Aha. So, again, not having read the paper, this is a good thing to point out, being you want to work with other people. You want to have multiple eyes on your project. Because publishing by yourself is hard. And like I could anticipate that one of the reasons why Dragon had a hard time publishing his the first go round of this manuscript was because like only his eyes were on it. And he was so used to his own work that, I mean, it's like looking at a crossword or like a word search for too long. When you look at it too long, you get used to it. And sometimes you need a fresh set of eyes. That'll help. And just like the more diverse your group is anyway, like the more ideas you'll have. Maybe one of the reviewers like was giving notes and like the new author was able to interpret them, uh, or like knew what the reviewer meant. I don't know. Like I often need other eyes when I do work, or um even to help me interpret like feedback. Like sometimes I'll get feedback. Um I've gotten feedback on exams before and stuff where I'm like, I don't even understand what this feedback means. I have to ask someone. Um One physicist who was immediately attracted. Oh, never mind. Blah 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 blah. The article's been downloaded a bunch of times. Most out of all of the papers published last year in the journal. Duo had and still have a fight on their hands to be taken seriously by the Court of Scientific Opinion. If they got through a peer-reviewed journal, then like that demonstrates a modicum of like acceptance. I don't know. That's also a weird line. Like I feel like this author is just drumming up drama that doesn't actually exist. Maybe there's a huge screw reputation. But actually, I agree with that statement. Screw reputation. Reputation's stupid. Um, One physicist who was immediately attracted to Dragon and Eckert's ideas of quantum information science was quantum information scientist Vlatko Vedral. After reading the article, Vedral, whose PhD mentor was Eckert in the past, invited Dragon to prevent virtual talks to his group at the University of Oxford. Generated a lot of excitement. What I liked about the approach is the frequency we think of imposing quantum mechanics on everything else. How do we make relativity comply with quantum mechanics? But they're trying to twist this around. I do like that. Like, I mean, this quote gets at the idea that you do need to be creative, you know? Like, again, doing the same thing over and over again. Like, if it's broke, don't fix it, but also maybe we could come up with something better. Maybe we could approach things from a different angle. I mean, I'm a physicist. I'm lazy. I'm always going to try and find the easiest, quickest, shortest route. Principle of least action. There are many others who are suspicious of any approach that doesn't place quantum physics front and center. Not only are crackpots with wild, unphysical concepts rife in this area of physics, we can talk about that. But deeply rooted in the community is the idea that mind-bending elements in quantum physics simply cannot be explained any further. They just are. Okay, so physics being full of crackpots is absolutely true. My at all of the universities I've been to, the department chair at each university has stories about like the community science, like science enthusiasts, science fans, I don't know, the people with theories who will like give them a call or shoot them an email and say, "Hi, I know you're the lead physicist at the university and I have a theory, I have an idea." Yeah, and it's like, okay, cool. And I'm not saying that these are like necessarily flat earther folks, but it's some of these people have very interesting and relatively unfounded physics ideas. Um, yeah, the other half of this sentiment, though, that like the mind-bending elements of quantum physics simply can't be explained any further, they just are. I mean, that's how all physics is, though. Like, it just is, and we, as like rational, critical thinking meat sacks with bones inside, one day myself, um, we we are the ones who are ascribing meaning to these rules. Like, the world exists and physics exists. The laws of nature exist, like, without humans. We are trying to give context. We are trying to create models and describe them. Describe them very often with mathematics, and it is beautiful, and I don't know if I would say convenient or intentional that the physics that we see in the world very neatly lines up with a lot of the mathematics we use to describe it. Um, but like it's just a description. Like it's a way for us to make sense and make predictions. So like science, like physics just is. So I don't. I mean, I always get bugged with this too when you'll hear the phrase like discovered new physics. And I don't like that phrase because it implies that the physics didn't exist before, but it did. We just have discovered a more accurate way, or a more like we have fine-tuned our model to describe something, or we there's a piece of our model that we weren't taking into consideration. Like, the physical world itself isn't changing, but we are developing better and new ways to describe that physical. So yeah, quantum physics just is. Gravity just is. Like, there just is. I don't know. I don't like that. Critics from this camp question both the assumptions and methods used, as you should, any paper. Now I have a coffee. You don't have to. Reagan discussed the ideas with one of the founding fathers of string theory, Holger Nelson. The main criticism was that faster than light matter would be unstable and therefore unphysical. Like, that's a fair criticism. I mean, like, I wouldn't even call it a criticism. It's just like pointing something out. I don't know. Another theoretical physicist who asked to remain anonymous thought that the pair had used mathematics that changes the vantage point from which you observe the physics in order to change the actual underlying physics itself, which it should never do. Okay, so that's actually a big deal, especially if you're using relativity. Um, it's called relativity because it's the science of relative viewpoints. So, like, changing which relative viewpoint you're using to observe something will drastically change how the model applies. That's, I mean, that's what makes relativity cool. That's what makes it fun, and where you get all these paradoxes like, I'm older than my grandpa and stuff, because the vantage point that you're at is fundamental. Uh, often These criticisms boil down to 2 points: that no one has ever detected anything racing beyond the speed of light. True. I mean, we've also, like, until not even. Oh, wow. Was the Higgs. The Higgs discovery is almost 10 years old. But like, we theorized the Higgs, but no one had ever. And like, technically, no one has ever seen it, but we've detected its decay. Like, I don't know. And that if anything did travel that fast, time travel is possible. Time travel leads to causal paradoxes. Most famous is the grandfather paradox, the idea that if you travel back in time and kill your grandfather, your own birth would be impossible, but then you wouldn't have been born to kill your grandpa. Yeah. Dragon and Eckert argue that these critics miss the point. We're not saying there are any objects that travel faster than there might be, but that doesn't enter our argument. What we are saying is that you can look on the world from a perspective that is beyond light speed. Sure. I can. Yeah, like you can do that. From this faster than light vantage point, you can swap the order of cause and effect. Okay, now this is getting weird. This is a key result because the underlying physics must remain the same regardless of whether you're watching events unfold above or below the cosmic speed limit. This is true, the pair argue, that the order of events no longer plays a fundamental role in. Okay. I mean, we'll get to the actual paper, but uh, Reagan says all of this means that there are no paradoxes to answer at all. Look at it carefully, you find that the rules of causality are changed. They are not completely destroyed, they are modified in precisely the way that quantum. What? Okay, what? The way that quantum theory tells us about causality? They admit that the paper is far from the end of the story. Stay tuned. Volume 2. They don't know whether or not they'll be able to truly derive quantum theory from special relativity. If they can, it'll transform the way that researchers. Yeah, this is always the thing. Popsci articles are like, if they can do it, it'll change the world. Yeah, if they can do it, we're gonna have flying cars on Mars and no cancer. And like, it's cool. It's cool, but um, okay. It'll transform researchers' approach reconciling special relativity's big brother, general relativity, with quantum mechanics. That's an interesting way to call special relativity the little brother. It's like, I don't know. I don't want to ascribe familial relation to physics theory. Special relativity is a special subset of general relativity. That's why it's called special. Because it's like a little bit general relativity. General. Physicists are very. All right. If you can convince me that quantum mechanics follows from relativity, then maybe I could reconsider what fundamental entities are in my theory. And maybe the road to a quantum version of general relativity is very different. Had COVID-19 not thrown the world into turmoil, Dragon and Eckert would be working on it right now in Singapore, but for the time they're happy simply railing against conformity. Okay. And this author is just like, Trying to drum up so much drama. Solve one of the most pernicious problems in modern physics. More work has to be done for sure, but what I like about this paper is that it's not boring, right? It will create emotions one way or another and serve as an opening paper for further investigation. Okay, that's a really interesting quote. Again, I haven't read the paper yet. We don't know what my emotions will be. This is just such a weird quote. Like, why would you? My work isn't boring. It's gonna like ruffle feathers. It's gonna create emotions. Like, no, just from what I know about all of the many physicists I've interacted with, they're very much of the like, I can't have a. I am pure logic and reason. And so like this feels like a I'm going to logic you into being mad. And it's I don't know. It feels kind of I'm getting petty vibes from it, but I don't know. I don't know either of these. Well, thank you, Condé Nast, for this article. And Benjamin. So, we can get to the actual paper called Quantum Principle of Relativity. This was published March of last year in the New Journal of Physics. What are you? I'm not familiar with this journal either. Let's look it up. New Journal of Physics. Let's see what Wikipedia says. The New Journal of Physics is an online-only, open-access, peer-reviewed scientific journal covering all aspects of physics as well as interdisciplinary topics where physics forms the central theme. The journal was established in 1998, joint publication of the Institute of Physics and Deutsche Physikalische Gesellschaft. I don't know sprechen Sie Deutsch. Okay. Published by IOP Publishing. The editor-in-chief is page does not exist. From the University of Calgary and Science and Technology, China. Okay. So, okay. So it's a peer-reviewed open access journal. So there are a couple cool things about this. One, it's online only and open access, which more scientific writing needs to be. Excuse me. Yeah. The publication fees and it's a racket. Academic journals are a racket. I love all of the jokes that are like, how could you not know that this thing about climate change was happening? All you had to do was pay the $2,000 yearly subscription fee for this journal to read the paper about it. Because that's kind of how it. Okay. I don't really know anything about this journal. So yeah, that's the thing is I don't know. It's definitely not nature. And it's not science. How many citations does this article have? Where do I look at that? Oh, references. Oh, five. Five things. One of them is an archive paper by the guy. By him. I'm guessing this is the one that got rejected twice. And then he just threw it on archive for himself. Preprint. Yeah, let's look at that. Reference. Um, the devil plays dice. I Okay, this is a personal qualm. I hate when people use the royal we when they wrote a paper by them goddamn selves. You. You did it. Okay, so my skepticism is increasing. Let's make this big. All you folks at home can see it, and let's dig on in. I'm gonna do that. Okay. Abstract. Quantum mechanics is an incredibly successful theory, and yet the statistical nature of its predictions is hard to accept and has been the subject of numerous debates. Okay? The notion of inherent randomness, something that happens without any cause, goes against our rational understanding of reality. Okay, so I got grumpy when the popsci article used the word randomness to describe quantum mechanics too. And I was like, it's probabilistic. Let's see. Like, Penguin of Doom, I have a spork. That's the only thing in this universe that is truly random. That's an old reference. Cut the clip. Shut it down. To add to the puzzle, randomness that appears in non-relativistic quantum theory tacitly respects relativity. For example, it makes instantaneous signaling impossible. That would be, for example, on my, oh no, that's thumbnails I'm working on for our YouTube. On my dinky little space-time diagram, instantaneous would mean like an event happens here at this physical position at this time, and by instantaneous, a different or connected event happens at the same time but at a different position, and like that is moving in space without moving in time at all. So that means no time has passed, but like the same thing, the same signal or event is happening in two separate physical locations that are connected. And that means there is like no travel time. Not even faster than light travel time. That is zero travel time. And that is like not how we work on space-time diagrams. Okay. Here, we argue that this is because the special theory of relativity can itself account for such random behavior. We show that the full mathematical structure of the Lorentz transformation, the one which includes the superluminal part, implies the emergence of non-deterministic dynamics, together with the complex probability amplitudes and multiple trajectories. This indicates that the connections between the two seemingly different theories are deeper and more subtle than previously thought. Okay, so what they're saying is that by taking the non-physical set of, like, the non-physical half of the equation, the faster than light chunk of our space-time diagram, they're saying that in that regime, they are finding things with probability amplitudes and multiple trajectories. And that because we have probability amplitudes and multiple trajectories in quantum mechanics, these must be related. That's what I'm getting from the abstract. All right. All initial observers. Full mathematical structure of the Lorentz transformations contain both a subluminal and superluminal terms. Superluminal part is discarded. That is subluminal, like lumens, light, slower than the speed of light, stuff, super faster than the superluminal part is usually discarded on the premise that it makes no physical sense. And I mentioned that earlier. Like, we discard physically nonsensical solutions all the time. All the time. You do it in kinematics when you get a negative time. It's not physical. You eat it. On the premise it makes no physical sense, and as a consequence, familiar classical picture of a particle moving along a well-defined path is obtained. Here we show that if we retain the superluminal terms and take the resulting mathematics of the Lorentz transformation seriously, why wouldn't you take it seriously? Let me take this math not seriously. Then the notion of the particle moving along the single path must be abandoned and replaced by a propagation along many paths, exactly like in quantum theory. Okay, so I'm going back to what my gut was feeling when we were reading the popsci article about how some scientists say that you can't explain it further, it just is. Because I'm not surprised. These two things might be completely unrelated. And they can, I'm not talking specifically about this situation, but in general, you can have two things that are very closely related mathematically, but physically, like, they don't resemble each other. For example, like Earth orbits and the Earth orbiting, like, the sun. All of those are based on a central, like, 1 over r squared force law. Electromagnetism also follows a 1 over r squared force law. So, like, we mathematically describe those forces very similarly, but, like, they are nothing like each other. Like, physically, gravity is very different from electricity. And the fact that they can be described with similar mathematics, I don't know. The physics just is. How we choose to describe it as scientists, like, I don't know. I don't know. Like, I can use addition to balance my checkbook, and I can also use addition to, I don't know. My analogy fell apart because I didn't. What I'm trying to say is that people who do math, like, the math that exists is gonna be related. Like, you're gonna see similarities in any model you do based on the fact that, like, this is math. Generalized blah 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 blah. Okay. The generalized Lorentz transformation can be derived in a few simple steps. Consider a classical 1 plus 1 dimensional case. The 1 plus 3 dimensional case will be discussed later. With an inertial frame t prime x prime moving with relative velocity v to the frame tx. Okay. So we've got two reference frames, and they have a difference in their relative speed. One is moving v relative to the other. We seek the most general form of the coordinate transformation between these two frames that is consistent with the Galilean principle of relativity. It has to be a linear transformation, so that no point in space-time is singled out, and its coefficient must depend only on the relative velocity v. Inverse transformation involves a sign flip in the velocity v, meaning that from the other reference frame, thing is moving. Okay. Oh, this is some high quality image. Like, I wonder if the PDF is better, but this is like, oof. Oof. Not a very pretty function. Okay. So what this is saying is that the a location in the primed reference frame is some function that depends on the velocity times the location in the unprimed frame, and a different function dependent on the velocity multiplied by the time of the unprimed frame. So it's a Lorentz transform. And the inverse requires inverse. Okay. Where a, v, and b, v are unknown functions which we wish to determine. The origin of the prime frame is 0. Moving according to the equation x equals vt. Its position equals its velocity times the time. Right? Putting that into 1, we obtain that v, negative v, equals the function b over the function a. So that is coming from, they're saying if this term is 0, wait. Okay, so they're saying that, oh, x is vt, and x prime is 0. So they said 0 equals a vt vt, and then they just solved for negative. Okay. Okay, that's fine. So now we have, now we know that the ratio of the time function to the space function parts of our transform are negative b. Put that back in, and we get this expression. Okay. At this stage, all we can say about AV is that it is either symmetric or anti-symmetric as a function. Yes. This is because a discrete sign change of any spacetime coordinate in the unprimed frame should also result in a discrete sign change in the transformation formulas. Okay. But since such a sign flip also affects the sign of the velocity, the quantity AV must be either symmetric or anti-symmetric. So they're saying if my reference, if I'm in the frame where my reference frame is left, my equation should also work this. Switch the sign of the velocity, all of the formulas should still, they must work. Because we want a symmetry there. Got a symmetry. Yeah. In order to determine A uniquely, consider 3 inertial reference frames. Okay, so we got a double prime in here. And let the prime frame move with velocity v1, and let the double prime frame move with velocity 2 relative to the primed one. So that means non-primed to double prime is going to be v1 plus v2. By iterating, we obtain the velocity of the double primed observer relative to the unprimed one. Okay. So, yeah, they've got a v1 times v2. And we've got v1 plus v2. Looking at the first equation in 2, we can see that we can compute v. We can calculate the relative velocity by calculating the ratios between the coefficient of t and the coefficient of x. Okay, so they're saying do this thing again. Find v over a. Applying this rule to 3, we obtain okay. Are they already using the superluminal part? Because they have a plus sign here. They don't have a negative sign. Like, are they already using? So I think we're already looking at the super, like we start off looking at the super. I don't know. Oh, okay. So this is just absolutely general. Okay. Looking at the first equation in 2, they compute and they get that b, the coefficient, okay, the ratio between the coefficient. Yep. Noticing the interchanging v1 and negative v2 should result in a velocity of the unprimed observer relative to the double primed observer, which is negative. If I switch, yeah. Yes. Okay. Equating 5 with 4. Okay, so you have an expression for v, you have an expression for negative. For any v1 and v2, this can be satisfied only if both sides of the equations are equal to constant, k. Okay. Which sets a constraint on possible functions for a. The symmetric case condition gives that, using the sign such that for v goes to 0, we get x prime goes to x. Right. If there's no relative velocity, then they're the same reference. Okay. So this is the symmetric case. The new constant k remains unknown. In the case of k equals 0, corresponds to the Galilean universe. K is bigger than 0, leads to relativistic spacetime as we know it. Yeah, this is beta. This is just a Lorentz transform. Yeah, this is just the Lorentz transform. This is gamma. They're just doing this in the most convoluted, hardest way possible. Like all of this, I don't want to do it, but I'm sure that like Tevian's book does a geometric derivation of it where he just draws a picture and is like, ta-da, Lorentz transform, and we'll call it gamma. This is overkill. So we've got this constant k corresponds blah blah blah. The last case of k smaller than 0 corresponds to Euclidean spacetime with one of the dimensions stretched by an extra factor of root k. The derived transformation being just a regular rotation. From now on, we pick k to equal 1 over c squared. Because v squared over c squared is beta. For those of you who've done special relativity, beta is It's a factor. It's your beta factor. Which brings us to the Lorentz transformations for well-behaved velocities of v less than c. Did they have a page like limit? Did they have to hit X amount of pages? Because like they could have started here. They could have just started here and said, these are the well-known solutions to the Lorentz transformation. Like this is okay. Okay. For the antisymmetric case, we get this different constraint, which is well behaved for v bigger than c and leads to the following transformations. Okay, so maybe they did all of that stuff to argue that the asymmetric case is what gives us well behaved functions for big velocities, which is fine. So far, we've only used the Galilean principle of relativity, which put no restrictions on the possible velocities of the observer. Both solutions preserve the consistency of the speed of light. In order to get rid of the second branch of solutions, the antisymmetric solutions, we have to introduce an additional physical assumption that rule them out. We choose not to do so. Instead, we investigate the physical consequences of these extra solutions. Fine. Like you could have started the paper here. But I digress. Two comments are in order. First, the sign in front of the equations cannot be uniquely determined because no v to 0 limit exists. The choice of sign must remain a matter of convention, and from now on we will pick the negative sign. Both branches of solutions must form a symmetry group only in the considered 1 plus 1 dimensional scenario. This is not the case in the 1 plus 3 dimensional scenario. Therefore, we will carefully discuss this case separately in section 5. For now, we stick to the 1 plus 1, in which the equation 9 describe a hyperbolic rotation by the angle pi fourths to 3 pi fourths. I mean, like pi fourths to 3 pi fourths. Ugh. So far, we have shown Galilean principle of activity leads to two branches of coordinate transforms. Okay. 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 These branches are indistinguishable, which means that a particle at rest with respect to an observer belonging to one branch will be considered superluminal by the observer belonging to the other branch. Being superluminal is relative. So they're saying that one branch might see something moving faster than the speed of light, but the other branch would not. That feels wrong, but suppose that a superluminal particle observed by some inertial observer was emitted from a source at event A and then absorbed a later time by the identical target particle at the event B. The same process observed from a reference frame moving with a relative subliminal velocity. Figure 1, where B becomes the emission of the and A the absorption. Okay. Space-time diagrams of a process of superluminal particle is seen by first time is A. Particle emitted from A and absorbed by B. Same process observed in a different. Looks like B sends it to Okay. So this is I my skepticism is increasing exponentially. They didn't draw axes on their diagram. They described their axes in the caption, but like, come on. Come on. Like, and you didn't tell me what the difference between these is. Like, this looks more like a Feynman diagram than anything else, which is probably what they're trying to do and say that this is all like, look, it's quantum mechanics, Feynman diagram. I. So. Uh, no, it's dashy, so it's a carrier. So. So what they're saying is that I could perceive events happen in an order, and someone moving relative to me could see the events happen in a different order, which is true. That can happen. That can happen in relativity. All right. Let me download this figure. Thank you, button. Actually, let's click on it. What does the high-res version of this look like? Oh, it actually is high-res. Wow. All right. Let's focus on the first frame and assume the moment of emission at A could be predicted. Let us assume that the past world line of the source prior to A contains locally all the information necessary to predict the exact moment. Okay, so we know exactly when our particle A is going to be emitted. Oh, God. I'm just going to read this out loud. Let us focus on the first frame shown in figure 1A and assume that the moment of emission at A could be predicted using a local and deterministic mode of description. In other words, let us assume that the past world line of the source particle prior to the event A contains locally all the information necessary to predict the exact moment of emission of a superluminal particle at A. Or, using the Einsteinian language, there is an element reality to it. You said the same sentence 3 times. I hate this. Let's focus on this. In other words, let's focus on this. Or as in Einsteinian language, let's focus on this. On the other hand, someone is holding a target on B cannot predict the moment of absorption at B based on local measurements of the particle B prior to the event. Okay, so A knows exactly when their little tachyon thing is going to get emitted, but B doesn't know when it's going to arrive. That's fine. Now let us change the reference frame and study the same scenario from the perspective of the observer moving with some subluminal speed, depicted in figure 1b, and ask the question, what caused the emission of the superluminal particle at the event B? We could say that the cause of the event B takes place in a distant world line of particle A, possibly at a later time than the event B itself. However, if we seek a deterministic and local mode of description, trying to determine the moment of emission at B only by a local measurement on the particle B, it is clearly impossible. We have already assumed that the past world line of B carries no information about the time of the event B. In practice, the observer only has access to local properties of the particle B and can only conclude that emission at B be completely spontaneous and fundamentally unpredictable. So they're saying that I can know information about A, but I can't know information about B. And so if the order of emission was flipped and the particle was emitted from B, or I'm in a reference frame such that I observe B happening first, I wouldn't know when it happened. And I would have to know information about A's event. The thing that I don't like about this is that it's treating this superluminal particle, this little like tachyon boy going between A and B, as they're using words like emission and absorption, which to me imply an action. Like absorption is distinct from emission. They're not saying the particle is at A at this point, and then the particle is at B at this point. And they even switch their language. They talk about the particle being emitted from B, which is very confusing. I think what they're trying to say is that I have a particle, and the world line of this particle like we have a particle, and the world line of this particle is faster than the speed of light. And so one reference frame could sees it leave here and go here, and another reference frame could see it go the other direction. Because if it's moving faster than the speed of light, it could look like it was going back in time. Okay, fine. We could say the cause of okay. And so what they're imposing here is that I know when the particle I can know when the particle leaves train station A, but I can't know when it arrives at train station B. And so, if I look at it from a different perspective, where I see it at train station B first on its journey to train station A, I see it like running backwards, and like I see the train running backwards in my reference frame. They're saying I can't know when it leaves station B to travel back to station A. Because it is deterministic based on stuff happening at station A. So if I know about station A, so I would know when it arrives at station A, but I don't know when it leaves station B. That's weird. Okay. We could say that the cause of B took place distantly on the world, possibly. Okay. However, if we seek a deterministic and local motive description, trying to determine the moment that B leaves the train station, I'm using leaves as a train station because I don't like this emission and absorption of superluminal particles. That's weird. Only by local measurement on the particle B. It is clearly impossible. We have already assumed that the past world line of train station B carries no information about the train coming to station B. In practice, the observer, having only access to the local properties of particle B, can only conclude that the emission at B was completely spontaneous and fundamentally unpredictable. Okay. So, this is saying that somebody at train station B has no idea when the train is going to leave station B, because they only know about train station B. However, someone at train station A knows when the train will arrive at station A. So the person at train station B says, I don't know why this train just left. The person at station A says, it left because it has to be here at 5 o'clock. Okay. We have previously assumed that the cause of emission of the particle, the cause of the train leaving station A in the first reference frame, was determined by the train schedule at A. Hi, Juno Kitty. This assumption leads, however, to a preferred reference frame. Yes, it does. Which is the local deterministic mode of a description is possible, while it remains impossible in other frames. It becomes especially clear if both particles A and B are identical. Okay, so if our train stations are indistinguishable, to preserve the Galilean principle of relativity, we have to abandon our assumption that the train leaving A in the first frame could be determined by a local process. As a result, we conclude that no relativistic, local, and deterministic descriptions of emission of a superluminal particle is possible in any inertial frame. Hey, friend. A friend. Gonna meow. Here. Okay, and so they're saying that this would make a preferred reference frame, and part of the point of relativity is that there is no preferential reference frame. There is no, or rather that physics should operate the same in any reference frame. If I'm in my car, if I'm on the street, if I'm sleeping in my bed, if I'm in a airplane, I should have physics should still work. Okay, so if such emission took place, it would appear random. If we had a source of superluminal particles at our disposal, we would not be able to use it to send any information because we would not be able to control the emission rate at any local operations. Okay, so they're saying that if we had faster than light particles, we wouldn't know when they were going to leave, because we also wouldn't know when they were going to arrive, and that we could know nothing about we have no information about when the trains leave the stations, any station, so it's not reliable. I just want to show you the desk cat. Say hi. What a heckin' cutie. Oh, your fat butt is pushing my mouse buttons. Please don't rub the mic like that. Non-deterministic behavior is not only a property of superluminal particles. It applies to subluminal particles. Consider a decay. All right, now we have a superluminal particle decaying into two subluminal particles. So we got a faster than light train breaking apart into two slower than light trains, as depicted in figure 2a. Let's picture the same process as seen by the infinitely fast moving inertial observer, for which the transformation reduces to space becomes time and time becomes space. You can't have an infinitely fast inertial observer. What? Paper's gonna make me need a glass of water. So, okay, they're saying we have an observer who's moving so fast that their space coordinate is my time coordinate, and my time coordinate is their space coordinate. We've just flipped the axes. They're moving so fast that the axes have been swapped. It's not physical, but okay. For such a frame, the considered decay process is depicted in figure 2b, where the particles are superluminal, and henceforth the decay cannot be described using any local and deterministic theory, as we have shown earlier. By invoking Galilean principle of relativity, we conclude that the same must be the case for the subluminal reference frame. Okay. Okay. Again, spacetime diagrams of a subluminal particle into a pair of subluminal. Time is vertical, space is horizontal. Subluminal reference frame in a super. All right. So, what this is doing is saying, here is my time, here is my space axis, which again, they could have drawn with literally 2 lines, but they chose not to. This is bad. If any of my students ever gave me diagrams that looked like this, they would get scathing notes from me. Absolutely scathing. This is unacceptable. So they're saying we've got this little doodle. You'll notice the slope is steeper than 1, meaning it is slower than the speed of light. And it breaks off into 2 particles that are also slower than the speed of light. Fine. Now they're saying if I have an observer who's moving so fast that their space and time transformation is completely flipped to mine, they would see a 90-degree rotated version of this where all the particles are moving faster than light. They all have slopes less than. But you can't. This isn't a thing. Like, there's no such thing as an inertial observer who is still inertial moving faster than the speed of light. Inertial Okay, so I understand what the critic that they quoted in the article was talking about with them, like, swapping reference frames in a way that is, like, doesn't feel right. I don't know, Brendan, do you have any thoughts about this? Yeah. Sure. If I allow an imaginary observer to move infinitely fast.
Of course.
Yeah. So basically, yeah, the mic didn't pick up any of what Brendan said. But basically, what he was saying is, okay, you let somebody move faster than the speed of light. You let them move infinite fast. They are covering all of the distance in none of the time. So fast. Of course, everything else in the universe is going to be moving past them at faster than the speed of light. Because, like, they're moving faster than the speed of light. Just like when I walk past a tree, it moves past me at walking speed. But if I'm in my car, it moves really hella fast past me. Congratulations, you're going fast. You can't have an observer who goes that fast. So this is kind of like, it's fun to play with, I guess, kind of. I don't know. Multiple paths. Another property of quantum theory, you haven't talked about quantum. Okay, besides it being non-deterministic, is the fact that a particle is not observed, behaves as if it were moving along multiple, which is best known for interference in 6. Okay, this is like the uncertainty principle that, like, you can't. Okay, but a particle is, once a particle is observed, it can only be detected in one. Okay, yeah, you collapse the wave function. And you can see it. And you know what it is. Now let us show how this follows from a Galilean principle of relativity involving both families of inertial observers. Consider a photon emitted from A, reflected from a mirror M, and then received at B. Suppose that we want to detect the photon by placing detectors in its path. If a detector is placed between A and M, absorbs the photon, then a similar detector placed in the path of M to B will not register anything because the photon has been absorbed earlier. You catch it in the net, the first net, it's not going to make it to the second net. Fine. Similarly, if the detector at M to B absorbed the photon, then certainly the photon was not detected A to M. Also, fine. This is how particle detectors work. You're not going to catch all of them, but you know you're going to catch some of them. Now let us analyze the same scenario. Ugh. Why are they doing this? Part of me feels like this paper got through. Yeah. Part of me feels like this paper got through because nobody wanted to, like, read this. I know I'm being kind of an asshole and these people are, like, professors at places, but they're making me feel emotions. They're making me feel emotion, like they said they would. In this reference frame, the photon is traveling from M towards A and B along two paths. But if we try to detect it using a pair of detectors, then only one of them can absorb the photon. However, as long as we do not make any observation, the motion of the photon is characterized by two simultaneous paths, not one. Okay. So again, we have an infinitely fast-moving observer, so our diagram, our space-time diagram, gets a rotation by 90 degrees. And so they're saying that both because this is upwards in time.
I know.
Yeah, I
How
don't.
did they justify the fact that they are?
I don't. Yeah, okay. They shouldn't have switched the direction of the arrows, I don't think. I don't think. Yeah, no. The arrows. Yeah, so it's going from A to M to B. They should have kept it A to M to B. But they're saying that because A happens later in time, you can't say that it came from A to M to B. Like, if you're going faster than the speed of light, if you're going infinitely fast, then, like, causality doesn't matter anyway. Like, we already knew this.
So the scenario they're, like, posing here. The scenario they're positing here is, like, I have an infinitely fast observer who functionally exists in the side light cone space.
Yeah.
That side light cone observer sees not just causes and effects, like, amorphously, like they don't make sense, is what they're trying to say here. That, like, the consequences of the space makes it so that they can't distinguish between, not only they can't distinguish, like, space and time's roles in the space become mixed and swapped specifically.
Yeah.
Right? And so, like,
things that are separated in space are now separated in time.
They're trying to say that if I'm in this totally not preferential reference, this is definitely a preferential reference.
Well, that's just it. Is they're trying to argue that it's if we have a non-preferential reference frame and we have, like, inertial observers in two different frames, then physics should work the same in both. But that doesn't happen if you literally swap time and space axes. Like,
so they're I think the way they're trying to say something about those arrows, superluminal observer still has so what they're saying is, like, global coordinate time moves by going
hmm?
they're trying to reimpose order of traditional light cone superluminal, who by the very nature of space and time being swapped should not have a correct understanding of what t increasing in the rest frame.
Yeah, because
so they have
this
no
is
reason.
x increasing in the rest frame is this direction, and they're saying that x increasing that is their time increasing.
They're still saying that time is increasing in the vertical direction. Right? So what they're trying to do is, like, if I had a superluminal observer and take data and plot what they see, and then I tried to interpret it, here's what it would be. But in doing so, they have scrubbed over the fact that, like, a rest frame observer can only understand this stuff going up, And so these arrows have to go in this direction. But the superluminal observer would not put these arrows in this. They go the way they used to. B goes backwards in time, and A goes forwards in time. That's the correct reading of the diagram that they presented here, and they just swapped the arrow so that.
I hate this.
So this is that arrow. That's a lie.
Yeah.
I will contest that is garbage. No way.
And their argument is that, well, physics has to work the same, so time moves forward.
No, you created an observer who lives in the preferential infinite speed frame, and it's preferential because it gives me
Nerds. Nerds. Oh, God. It gets worse. Okay, as we can see, even if we start with the idea of a classical particle moving along a single path, it's only a matter of change of reference frame to arrive at a scenario involving more than one path.
So, but you can only get two paths, right? So, they took...
No, if I shine a light beam in a million different directions and then I switch sideways...
They took a reflection and turned it into we reinterpreted the
I'm not being picked up at all.
We'll just point it towards me. They took the situation that was the superluminal observer and the data that came from the superluminal observer watching a reflection and said this now represents multiple paths. But that is still a cause and effect relationship that you are messing with to get this idea of there being multiple outcomes. And the only reason you arrive at multiple outcomes is because you flipped one of the arrows. I see you flipped an arrow. But you can't pretend that the superluminal observer watching all of the different reference frames that could exist is somehow multiple paths. That's literally what this bottom diagram, this part A is saying, right? This A graph is, they're saying that a particle emitted at A scatters, but it has two different paths and two different reference frames. And if you try and make that same argument, that superluminal argument, right? Then you're gonna, if I rotated this, right, then I have three paths. Like three different.
I have A and B prime.
Yeah. And but then like what is your statement, right? Your statement is that I have this event, which is this nonsense thing happening at the origin.
You have a decay.
Right, I have a decay, and my decay can either turn into probabilistically two different reference frames or the thing that it decayed out of. So like the implication is that your decays can go backwards.
No, get your butt off the keyboard. No, get your...
Things don't spontaneously turn into less probabilistic particles.
But that's their argument though, is that like things are less, because they're random. They haven't used probabilistic, they've used random because they're not. Yeah, no. Also, okay, so they scatter a particle which starts to follow two paths at once. It'll look like but it's different particles. Like, are they saying that particle A is indistinguishable from the particle it decays into? No, there are not particles that decay into themselves. Like, that doesn't happen.
Maybe what they're saying, diagram wrong?
No.
The scatter happens in a particle is emitted in A. Scattering event occurs at point alpha, and then either C B or B prime, depending on.
Okay. A is scattered at alpha, where it starts to follow two paths at once towards B and B prime. Okay, so it is the same particle. It is one particle.
Oh, no, I was right the first time.
Yeah, no, you were right. This is not. The same process viewed from the fast observer will see a particle following 3 paths at once. No! This concept can be iterated to scenarios involving multiple paths at once. Okay. I mean, part of the problem here is that in that first case with the photon bouncing off the mirror, they're saying for my specific photon, if I caught it in the first net, I know it won't get to the second net. Like, but when you, oh, okay. Okay. All right. Let's keep going. As long as you don't observe it. I wish I didn't observe it. I wish I hadn't had eyes to read this. Okay, let's keep going. Once both branches of transformations are involved, the classical description of a particle always moving along a single trajectory becomes inconsistent with the Galilean principle of relativity. Particle A is scattered and goes along 2 different paths at once. If it's not a decay, how can it be going, like, one observer is not going to see the same particle go to 2 different places? I'm sorry, that's not going to happen. Like, if I'm an inertial observer here and I see this particle scatter, it either decays into 2 particles or it bounces. But I don't see the same particle in 2 places at once. This is silly. Multiple paths connecting to, and okay, what is this though? Like, what is this diagram? This was, like, this is some back of the napkin ass drawings. I'm salty. Let us go back to the orthodox setting of subliminal particles being observed by subliminal observers. Thank you, God. Relativistic theories operate on notions that do not change under Lorentz transformations. Yes, that's what it means to be like an inertial observer. The laws of physics, if Lorentz transform, still happen. We will investigate what relativistic invariant quantities describe particle in motion between 2 points, A and B, that have properties of probability. Okay, so they're talking about proper time. They're talking about the energy. They're saying that the energy of the particle is gamma and the momentum of the particle is v times gamma, or proportional to. Okay. They're trying to say that they have invariant. They're now doing like invariant path integrals. Now they're doing the 3-dimensional case. I'm skipping that. I don't want to like go through their bullshit math because it's not going to add anything to the paper except that they're talking about how you write paths as path integrals. Okay. We argue that ruling out the superluminal family of observers from special relativity, regardless of whether such observers exist or not, is not necessary. It leads to a classical description of a particle moving along a well-defined single trajectory. In contrast, if one keeps both solutions, the non-deterministic behavior and non-classical motion of a particle arises as a natural consequence. Faster-than-light solutions appear naturally in general relativity. For instance, the Schwarzschild solution to the Einstein equations written in Schwarzschild coordinates has a peculiar property that the time and radial coordinate change their metric signs at the event horizon. Is that peculiar? I guess. Maybe it's not peculiar because it's not like, has never been anything novel to me. That's always how it's been. This is normally dismissed by arbitrarily stating that the Schwarzschild solutions only make sense above the event horizon. Well, have you seen inside a black hole? I haven't. I don't know if they're the same inside. Maybe we need completely different mathematics to describe inside a black hole. Maybe the solutions still hold inside. I don't know. I don't think we can ever know. Actually, no, I volunteer. Just yeet me. Yeet me right into the middle of the galaxy. I'll go. I'll explore a black hole. Spaghettify me. Okay. Normally this is dismissed. Although written in freely falling Kruskal coordinates, they are smooth at the horizon. In order to resolve this puzzle, we point out the Schwarzschild coordinates correspond to stationary observers placed at fixed distances from the horizon. Yes, such observers can be subluminal only above the horizon. Yes, because if you were inside the black hole, theoretically you would continue to fall faster onto the speed of light. So everything outside the black hole would seem to be moving faster at the speed of light than you. The time's different inside. The sign flip in the metric therefore signifies the transition from a subluminal to a superluminal family of stationary observers residing under the event horizon in a fixed distance from the singularity. Okay. We believe our approach is more than a mathematical exercise, and if taken seriously, may offer new valuable insights into deep connections between quantum theory and special relativity. What did you do in this paper? This did nothing. Oh my God. I was like, okay, I was giving them so much benefit of the doubt. I'm going to go rewatch this VOD and see how nice I was to these, what the article chose not to call them, crackpots. You don't even tell me anything. Like, this doesn't... Your summary is that you can flip metric signs and put space-time diagrams sideways, and if you try to interpret a sideways space-time diagram, it is quantum mechanics? Like, I'm sorry. Maybe I'm just absolutely dumber than a sack of potatoes. But I don't... What? The mic didn't pick that up, but I'm going to repeat it. Brendan said, what did you say? No one with an actual theory puts "if taken seriously" in their manuscript. Like, I feel like I'm being punked. I feel like they wrote this as like for shits and giggles. Like, wouldn't it be funny if? Like, this reminds me a lot. You know, maybe I'll read this paper next week. It reminds me of a theoretical paper I read, which, if I recall correctly, was very much of the attitude for shits and giggles, where the author was like, what if we had negative mass? What would that look like? And like, they just wrote a paper exploring this idea of like negatively charged mass. And it was fun. It was a fun little investigation. But like, that's all it was. And it was interesting, but like, it held more water than this. Like, there are so many... How do these people have professorships and I am like tearing my hair out at grad school because it's like the worst place in the world? Real Maggie opinion hours right now. This was something I was going to point out during the popsci article, and I didn't. And I am absolutely going to point it out now. Every single person mentioned in that article, the people writing this paper, the people that they collaborated with and talked to, the people who were critiquing them, all men. And I'm going to infer from their names all white men. Like, if I, and the guy complained that he had gotten his paper rejected twice. Fine. I talked about how that happens in academia. Like, you're gonna get your papers rejected. But if I had written this, like, if a woman had written this, there's no way. I hate physicists. Anyway, so maybe I will share the VOD of this with my grandpa who sent me the article, and maybe I won't. I don't know. This was an interesting day, though. We talked about pop science articles and how they sensationalize things. And I commented many times while we read that how dramatic that author was and how much controversy they were trying to imbue into their writing. Like, they tried to make it so dramatic. And, like, I didn't even read 2 of the sections of this paper because they so thoroughly lost my trust in what they were doing. Like, they spent the first fifth deriving something that they didn't need to derive, and then tried to, like, sweep their arrow switching under the rug. Like, man, I'm mad. I even got dressed up for this. I put on